All right. I'll chat about homework stuff later when more people show up because I'm a little light on attendance right now. So, um, anyway, let's continue on with elementary matrices. But before we start, are there any questions about anything? Things are going okay? Should have some web assign due on Sunday night. It was originally due last night, but I moved the date because we didn't finish up the section yet. So, all right. What's that? That's not the other one. It's you want this one. There you go. Yep. That's the new one that'll be starting here later. All right. So we talked about elementary matrices. We talked about the fact that when we do the multiplication by the elementary matrix on the left, it accomplishes the same row operation that you would have done with the original matrix. And we're going to use that idea here in a little bit to help us talk about a different method of solving systems of equations. Before we get there, let's make a new definition here for row equivalent. All we mean by two matrices being row equivalent is if there's a sequence of operations of or elementary row operations, I should say, that I'll say turn A into B. So if I can do a bunch of elementary row operations to A and end up with B, then I get what we refer to as being row equivalent matrices. So since we can accomplish this through, since we can accomplish this through multiplication by elementary matrices, what we can do here is say that I can take A, I can multiply it on the left by a sequence of elementary matrices. I'll call them E1 through En. When I do that product, we end up with B. Now, I wrote the subscripts backwards for a reason. Because if I think about E1 representing the first row operation that you do, and then E2 being the second one, I have to multiply on the left by E1 first, and then multiply on the left again by E2. I love the reverse order. So E1 would represent the first row operation you do, E2 would represent the second row operation you do, and so on down the line. So notice that from what we talked about last time, if A is row equivalent to B, we can also flip that around and say B is row equivalent to A. I can multiply both sides by the inverse of that product and get A would be the inverse of that product. And then from what we talked about before, how do you write the inverse of a product? What do you do? We wrote it as AB inverse equals something. Good. Yeah. It's the product of the inverses, but you have to reverse the order. And that works for any length of product that you have. So this would be E1 inverse, E2 inverse, En inverse times B. And we know that from what we talked about last time right at the end of class, that the inverse of any elementary matrix is also an elementary matrix. So now I've got a sequence of elementary matrices multiplied by B, and that gives me A. So then I also get B as row equivalent to A then. And it kind of makes sense that you have to do it in the reverse order, right? If I do row operation 1, then 2, and then the last one at the end, I've got to undo them backward, right? Yeah. The last thing you did is the first thing you have to undo. So that's exactly why they're written in this order. All right. So anyway, for those of you who have had discrete math, row equivalence is an equivalence relation on a set of matrices. They all have to have the same size, but being row equivalent is an equivalence relation. Remember, equivalence relation is something that's reflexive, symmetric, and transitive. So, anyway, all right. So going back to mega theorem a little bit, I actually flip-flopped a couple of ones that I wanted to put in here, but there's two other ones that we can add in here. Remember we talked about last time, we put at the end that the reduced row echelon form of a matrix is the identity, is it invertible? To that, I don't remember what letter I used for that one, but to that one you could also say now A is row equivalent to I, using this language. I can spell. So wherever you've got the reduced row echelon form of A as I, you can put in parentheses A is row equivalent to I, means the same thing. One that I forgot to write down, which goes along with that idea of having a unique solution. Remember, one of the equivalent conditions we had was that AX equals B has a unique solution no matter what the B is on the right-hand side. Well, what if you did the homogeneous solution, or a solution to a homogeneous system? If it's unique, what does the solution have to be if A is invertible? What would the solution have to be for AX equals 0? Well, if it's invertible, what's the only solution you get? What has to be a solution to any homogeneous system, no matter what, always? 0 does, right? If it's unique, then that's the only one, right? So another equivalent condition that you can put in your list is that the homogeneous system has only the trivial solution. That's equivalent to the matrix being invertible. Yep, add it to your list that you have. Yep, absolutely. Please add this to the list that we have. Like I said, we're going to end up with like 20 by the time we're done. The last one here that we're going to put in here is related to row equivalence. Notice that if A is row equivalent to I, that means I can write the A as a bunch of these elementary matrices times I. Right? That's what it means to be row equivalent. Well, anything times I is just what I started with. So now I have A as a product of elementary matrices. So that's another equivalent condition, is that A is can be written as a product of elementary matrices. Matrices. So let's see if we have an example that tells us how to do that. All right. So we've got a matrix here, 3 by 3. Pardon me. We want to write this matrix as a product of elementary matrices, if possible. If it's not invertible, then it's not possible. Okay? As we just said a second ago, being able to write the matrix as a product of elementary matrices means it has an inverse as well. And that was that whole idea of the following are equivalent. All those statements say the same thing. So the first thing we're going to do is what we've been doing all in the previous section with just finding the inverse. So let's find the inverse of this matrix. What operation would you do first here? What do we want to get first? Yeah, let's do a row swap, get a 1 up in the upper left-hand corner. Let's swap row 1 and row 3. And let's make sure that I can keep track of everything. So we'll swap row 1 and row 3. The 1, 1, 3, 0, 0, 1 goes on the top. The 2, 1, 1, 1, 0, 0 goes on the bottom. Is that okay? Yeah? All right. What's next?
2 row 1 plus row 2 replaces row 2.
Okay. So 2 row 1 added to row 2, we get 0, 5, 6. All right. That's 6. 6, 26. And then 0, 1, 2. Yes.
Could we just have added row 2 and row 3?
You could absolutely do row 2 and row 3 to get a 0 in one of them. Yeah. You'll still have to use the first row to get the other one, but yeah, you can get one of them. Yep, you can absolutely do that. Nothing wrong with that at all. What's the other row operation we should do now?
Negative 2 row 1 plus row 3.
Good. Maybe I can get it R. So 0, negative 2 plus 1 is negative 1. Negative 6 plus 1 is negative 5. 1, 0, negative 2. Next step is to get you need 1 in the middle here, right?
So 1/5 R2.
I could do 1/5 of our row 2. It'll give me some fractions. How could I avoid fractions?
Swap.
Yeah, let's swap row 2 and row 3 because that one already has a 1 there. That's what I would do. You can do the 1/5. There's nothing wrong with doing the 1/5. I'm just trying to avoid the fractions if I can. Okay. For a particular reason of I'm already having enough trouble doing the arithmetic, I don't want to do it with the fractions too. Okay. 0, 1, 2. And then multiply by negative 1. Good. Now that I have the 1, what's next? Okay. And then also, if we wanted to go ahead and get one of rid of the thing in row 3, we'll do. Good. Good. So do negative of row 2, add it to row 1, and do negative 5 row 2 and add it to row 3. Oops, it doesn't change the middle row. It does change the other 2 rows. So I get a 0 here. Negative 5 plus 3 is negative 2. Positive 1, still a 0, and negative 1. Get a 1 when I add down there, a positive 5, a 1, and a negative 8. It is a funky looking 5. Almost done. We got a 1 already down in the lower right corner. So now we gotta need to do the last 2. Got to get zeros above it, right? Okay.
Negative 5 R3 plus row 2 row 2.
Good.
And then 2 row 3 plus row 1.
Yep. Good. Good. So it looks like this is going to be invertible, right? Because we already know that we've got a pivot down the diagonal there, right? There's a pivot in every row, pivot in every column. We're good. So let's go up here. Oops, this row is the same. Nope, not that row is not the same. Sorry, I already wrote down what I wanted. 2 times 5 plus 1 gives me 11. 2 times 1 plus 0 gives me 2. 2 times negative 8 minus 1 gives me negative 17. Negative 25 minus 1 gives me negative 26, negative 5, and is that 42? All right. So now we know what the inverse is, right? We agree? Whatever the original matrix was, we know that that's the inverse. Okay. Remember, the goal of this problem, though, wasn't necessarily to find the inverse. It was to write the matrix as a product of elementary matrices, right? Okay. So how do we do that? Good question. Well, we just found a sequence of row operations that turned our original matrix into the identity matrix, right? So if I go back up here and start with I got to write it on the left. It's going to be a long sequence. All right. So the original matrix was, stop it, 2, 1, 1. No, yeah, it was 2, 1, 1, negative 2, 3, 20, and 1, 1, 3. Right? What was the first thing we did? Swap row 1 and row 3. What elementary matrix accomplishes that feat? Yeah, 0, 0, 1. Remember, it's the identity matrix with that same exact row operation. That's exactly right. Yep. Okay. What was the next row operation we did? Okay. 2 row 1 plus row 2 replace row 2. What elementary matrix accomplishes that feat? So we got to start with the identity matrix and do one row operation, right? So 1 with 0, 0 will be your first row. What will be the next row? 2, 1, 0, 0, 0, 1, right? That was this. So this, I'm going to label them. Here was row operation 1. Here's matrix 1. Here's row operation 2. Here's matrix 2. Next row operation was what? Okay, and so what matrix is going to do? What elementary matrix will accomplish that feat?
0, 1, 0, negative 2, 0, 1.
Good. And so that was the third one. Definitely want to label these because I don't have enough room. Okay. So this should keep going to the left. I ran out of room. The next one is, swap row 2 and row 3. So what matrix is going to do that? Good. Long string of things. Next one.
Negative R2 plus R1. Switch to R1. So that would be.
I think we skipped one.
Nope. Oh, yeah. Negative R. Swap row 2. Negative
Okay.
R2, R2.
Okay, so what matrix?
1, 2, 2. No. 0, 0, 1, 0, 1. I mean, 0, 1, 0. Negative 1, 0.
There we go.
0, 0, 0.
There we go. So that's this one. Only 4 more to go. The next one.
1, negative 1, 0.
Oops. Looks like I did 1 minus 1.
0, 1, 0. 0, 0, 1.
Okay. And the next one.
1, 0, 0. 0, 1, 0. 0, negative, or 5.
It was negative 5. Yep. Okay. That was this one down here. We see where these are coming from, right? We're literally doing the exact same row operation. We're just doing it to the identity each time, right? We haven't changed the row operation. Start with the identity matrix and literally do the exact same row operation that I have labeled. We've got 2 more to go. Like I said, I did leave myself a lot of room here, but that's okay. We'll figure it out. The next one was 2 row 3 plus row 1. Replace row 1.
So 1, 0, -2.
It's literally the exact same row operation, so it'll be a
2.
A 2. Good.
And then 0, 1, 0, and then 0, 0, 1.
Good. And that's operation 8. Last one was -5 row 3 plus row 2.
1, 0, 0. 0, 1, 5, -5.
Okay. Good. All right, cool. And that was the last one. When we do this big long product, what matrix do we end up with? The identity. Good. Yep. Good. Yeah, when we're done, we end up with this, right? Okay. So I know it was a long-winded way to get there, but let's look at what we have. This is our original matrix. Then we applied 9 row operations to get to the identity matrix. The point of the problem was the original matrix. We wanted it to be written as a product of elementary matrices. So what do I want to do to this equation that I have to get this being written as a product of elementary matrices? Yeah, we need to multiply by the. I want to undo all of those things, right? So I want to multiply by their inverses, right? Yeah. All right. So let's do that. So my original matrix here is 2, 1, 1, -2, 3, 20, 1, 1, 3. Oops, not inverse. What matrix is going to go first? Which inverse is going to go first in my list? 1. Yeah. It'll be the reverse order, right? This went from 9 down to 1. The inverses will be from 1 up to 9. It'll be in the reverse order here. Okay. What is the inverse of a row swap? It's the same, right? So I get 0, 0, 1, 0, 1, 0, 1, 0, 0. This was the inverse of 1. What's next? How do I undo adding 2 to row 2? Yeah, I need to subtract it, right? So what elementary matrix is going to go there?
The second one. No?
Yeah, I'm doing the second one, but what I have to do the inverse. So what matrix is going to go there?
-2, 1, 0.
There you go.
0, 0.
Yeah, that undoes it, right? That's the inverse of number 2 there. Now I got to undo 3. Good, yep. Next. It's 4, yeah.
1, 0, 0. 0, 0, 1.
Good. Remember, when it's a row swap, the inverse is just itself, right? The idea is to undo a swap. I can just do the exact same swap again, right? So that's the inverse of 4. What about 5? Well, yeah, that's fine. You're good. Okay. Notice that in number 5, it's a scalar multiple of a row. So you would do 1 over that scalar, but it's -1. So 1 over -1 is the same thing. So I get the same matrix again. We're almost done. Only have 4 more to go. What's next? Remember, for number 5, we multiplied by a scalar. We didn't add it to another row. Right, so I have to undo multiplication by -1, which is just multiplying by -1 again. Or dividing by -1, if you want to think about it that way. Yeah. Anytime it's a scalar multiple, it'll be 1 over that scalar in the same row. So if it were a 2, we would have used a 1/2. Yeah. Okay. Next one.
1 1 0 0 1 0 0 0.
Good. Next one.
1 1 what 0 0 0 1 0 0 5.
Good. And I can't see it. There it is. 8's up there. 1 0 2, so it'll be 1 0 -2. And the last one was a -5 in row 2, so it'll be 5. Yep. I know that may have seemed pointless for right now, but we really are headed somewhere, I promise. The process okay? We're going to use it here in a minute to solve some equations. All right. So again, the process is do the inverse like we always, to find this as a product of elementary matrices. Do the inverse like we always have. All right. Keep track of your row operations. Originally, I wrote this step here so that you could see that when you do this product, we get the identity, so we're undoing that product. If you want to, and you keep track of your row operations, you can literally just write the inverses of them here in order, right? The first thing we did was a row swap. This is the inverse of the second thing we did. This is the inverse of the third thing we did, and so on down the line. So you didn't have to write this step first. I was showing this step to show you where this step comes from. Okay. So if you're going through your row operations and taking your inverse, you can keep track of these matrices as you go along in that order. Does that make sense? Okay. All right. So how do we do a practical use of this? Because this seems like it was pointless, right? All right. So this has applications to solving systems of equations a little bit more efficiently. And we do this with the what we refer to as an LU decomposition, or a factorization, whichever way you want to call it. So what do we mean by an LU factorization? Or again, you might hear the words decomposition rather than factorization. The idea is that we write the matrix A as L times U, where L is lower triangular and U is upper triangular. All right. Now, when you're doing these LU decompositions, just as a heads up, you don't ever do a row swap. Okay? The reason why is if you do a row swap, notice you've got a 1, you'll get a 1 below where it's supposed to be for upper triangular, and then one other one that's above where it's supposed to be for lower triangular. Okay? So when you're doing LU decompositions, you'll never do a row swap. Okay? There is something that's referred to as a PLU factorization, or the P stands for permutation, and what it does is it sticks all your row swaps first so that you can make an LU decomposition. We're not going to do those. Just telling you that in general, when you do an LU decomposition, you're never going to do a row swap, or you're just going to say you can't do the LU decomposition. Okay. The other part's more than what I want to do. All right. So how do we do this? All right. So I want to convert this matrix into an upper triangular matrix using row operations. So we want to do Gaussian elimination. I'm just not going to worry about eliminating things above the diagonal. Okay? So if I want to turn that into an upper triangular matrix, no row swaps, let's just go through our operations like we always do. Pardon me. If we do that here, the first thing we would do is I would do 1/5 row 1 replace row 1, right? Make that a 1. We agree? Okay. So you get 1, -1, 2, 7. I don't need to worry about augmenting the identity matrix on here, by the way. Okay. I'm not worried about trying to find the inverse or solve a system or anything like that. Okay. So I don't need to worry about augmenting anything right this second. Okay. The next step will be -2 row 1 added to row 2 replace row 2. 1, -1, 0, 10 looks like. Not 10. 9. 2 times 1 is 2, not 3. All right. This is now upper triangular. Okay. Usually we make a choice when we do an LU decomposition. Either we put 1s down the diagonal for the lower triangular matrix, or we put 1s down the diagonal for the upper triangular matrix. So in this case, I'm going to put 1s down the diagonal for the upper triangular. I'll do 1/9 row 2, replace row 2. This is now my U for my LU decomposition. Okay. So when you go through the row operations, this is now the U that we're going to use for the LU decomposition. So the challenge is, and it's not exceptionally challenging at this point, but the challenge is to figure out what the L is. What the L it is. Anyway. All right. So let's think about what we just did. We started with the matrix 5, -5, 2, 7. We ended with the matrix 1, -1, 0, 1 by doing a series of row operations, right? The first thing we did was multiplied row 1 by 1/5, right? And then we multiplied row 1 by -2 and added to row 2. And then we did 1/9 of row 2. That was the row operations we did, isn't it? Notice that everything that we've put on the left-hand side here is lower triangular. The only non-zero pieces you see are below the diagonal, right? Now you had a homework problem that said products of upper triangulars is upper triangular. The same thing works for lower triangular. So if I multiply these things together, I'll get a lower triangular matrix. It's just on the wrong side, right? I'm supposed to have original matrix equals LU, not L times original matrix equals U, right? Okay. So I want to move all of these to the other side. But each of these is elementary matrices, so we know how to do those inverses, right? So when we move them to the other side, we're going to put them on the left because we'll be multiplying on the left to get rid of the inverses. The first matrix we'll have is 5, 0, 0, 1. The next matrix you'll have is 1, 0, 2, 1. And the next one will be 1, 0, 0, 9. And then still times your 1, negative 1, 0, 1. Remember what we just did in that previous example? When we do the inverses, we do them in the reverse order, right? So this is the inverse of what we did first. This is the inverse of what we did second. This is the inverse of what we did third. Now multiply those matrices together. These matrices together. What do we get? The first two we multiply together, we'll get 5, 0, 2, 1. Oops. And then do the next two, and we'll get 5, 0, and 2, and 9. If I did my arithmetic right, I should be able to get the same answer if I multiply these two together. Now, do you see I have a lower triangular matrix times an upper triangular matrix? Yeah, so this is your LU decomposition. Okay? So what were the steps here that we did? The first thing we did was put the matrix into row echelon form, right? Not reduced row echelon form. We didn't get zeros above the diagonal. We just got zeros below the diagonal. So we put it in row echelon form. That's the U, right? The U is the row echelon form. We did the inverse of the row operations and wrote them as elementary row operation, elementary matrices, and multiplied them together, and that's the L. That's how we do this, and we'll do another example here in a minute. But that's the sequence for putting this into an LU decomposition. So, how do we use this? Well, let's just do an example using this particular matrix. I might have it lower, but let's do this before I write down the steps. Let's say you wanted to solve 5, negative 5, 2, 7 times xy equals, I'll just make up some numbers here. It doesn't matter. It might be fractions, but I want to set it equal to 1, negative 2. Say I wanted to solve this system. Okay? Well, now that I have the LU decomposition, I can now write it like this. Right? I can replace the original matrix with that product. Right? Look at this. If you multiply this out, these two. If you multiply these two out, what size of matrix will you have? 2 by 1, right? Okay. Pardon me. If I have that as a 2 by 1, it's still going to have some x's and y's. So ignore the x's and y's for the time being. Let's just say I have some matrix 5029 times some other letters. Maybe I'll use a U and a V. I probably should have used another number besides 1 and negative 2, but that's okay. Can you solve this system pretty easily? What does basically the first row say? 5U equals 1, right? In the second row, if I use the second row, I would have 2U plus 9V equals negative 2. Remember we talked about using back substitution to solve a system if we have it in row echelon form? Here we're using what we refer to as forward substitution. Because why? What would I solve for first? U, yeah. And then plug it in here. What do we get? 2/5. I'd subtract it over, so you get negative 12/5. And divided by 9 would give you, what, negative 4/15. If I did that right. So I said I should have used better. I should have paid a little more attention to my numbers, but it's okay. So far, so good. This looks like the back substitution stuff that we did before, right? We're just doing it forward direction. Okay? But U and V isn't what I wanted. X and Y is what I wanted, right? What did I let equal U and V? Well, whatever the first thing for this one was and the first thing for this one was when I multiplied, right? So now we can solve 1, -1, 0, 1 times xy. That's supposed to equal 1/5 -4/15. Sorry. We replaced this with the UV and figured out what the UV had to be. Now we can figure out what the XY is to get those numbers. What equations come out of that?
X minus 5 equals 1/5.
Okay. And the second one is?
Y equals.
And then we can use back substitution now to solve. Right? I know what Y is. So my X will be, I'd add the Y over, so it's 4/15 plus 3/15, so it'll give you 7/15 when you're done. So that would be your solution. So when you have the LU decomposition, we can solve with forward substitution the lower triangular system and then solve back substitution to find the upper triangular system. Okay? All right. All right. So what's the process? So the first thing we're going to do is, if we're going to solve a system of linear equations, the first thing we're going to do is we're going to write A as LU. Okay, that's step one. Write A as LU. And the idea is to solve LU some vector X equals B. Okay. So step two is let UX equal some Y, call it Y, and solve LY equals B using forward substitution. And then take that solution for whatever the Y is and solve UY equals B using back substitution. Okay. Find your LU decomposition, solve L times something equals B using forward substitution, take that result and solve U times that solution equals B using back substitution. Whatever you get there. All right. This would be UX. Sorry. I wrote that wrong. This is not a B. This is a Y. I wrote the wrong letters. Sorry. Let's do another example. Sounds like you got a plan, doesn't it? Do another example. Sound like a good plan? Okay. Write this as a matrix equation first. What would the matrix equation look like? Okay. Okay. Good. All right. There's our matrix equation. First thing we need to do is get an LU decomposition for this. And again, it's tempting, but do not use row swaps. Row swaps will not give you an LU decomposition. Okay? So even though it's tempting to swap the rows here in a second, because of that 1, don't do it. Okay? 2, 8, -1, -1. Step 1. Can you do it? Okay, so I can't work up because I won't get a lower triangular matrix. I always have to work down. You're right, that'll make it a 1, but that won't work for the LU decomposition, unfortunately. Yeah, I have to do row 1 by a half. Good. I know it's tempting to try to avoid the fractions, but you can't do it the other way because the elementary matrix will be upper triangular. We want all of our elementary matrices to be lower, okay? All right, so what do we get then? We'll get 1, 4, -1, -1. What's next? Okay. And then again, if we want all 1s down the diagonal for our upper triangular, what will we do next? Good, good. Yep. All right. So 1, 4, 0, 1. Good. All right. So this will be the U, right? That'll be the U. That'll be the upper triangular matrix. Okay. How do we find the lower? Well, we've got 3 row operations that we have to undo, right? The first one is what?
2, 0, 0, 1.
Good. The second one will be
1, 0, 1.
I agree with that one. I have to undo it. -1. And the next one will be
3. Oh, wait, no. 1, 0, 3. No?
there's a 3 comes in. Yeah, but we're multiplying row 2 by 3. Oh, we multiplied by a third. We have to undo it. You can check your answer, right?
Why is the 3 on the right in that box? I agree that like a percent of
Which one?
on the last one. This was 1, 0.
Remember, it's you do the same operation as the identity matrix. The identity matrix is 1, 0, 0, 1.
Okay. Yeah.
So it has to be a 3 there.
Yeah.
Yep. Now multiply your matrices together. This one's going to be when I multiply the first 2 together, you'll get 2, 0, 0, 2, 0. Sorry, -1, 1. And then the next one, if you multiply together, you'll get 2, 0, -1, 3.
Wait, what did you just do?
I just multiplied straight across. I did multiply these 2 together first, and then took the answer. I multiplied the first 2 matrices together to get that one, and then multiply by the last one. Okay. Yep. All right. So the first thing we do again is we solve the lower triangular times some dummy variables. I called them U and V. You can call them whatever you want. I don't care. And that equals the constants that we're given. So what equations do you get out of that? I know we're out of time. What equations do we get? 2U equals -2 and good. So this one tells us that U equals -1. And if you put -1 in for U, and that makes it +1. Subtract it, you'll get a +1. Divide by 3, you're going to get V equals a third. It's like. Okay. And then you take your upper and use that now for the right-hand side of your equation. So what does, reading that straight off, what does y have to be? 1/3, right? Because that says y equals 1/3. This is why I was making those ones down the diagonal, by the way, because it makes this last part pretty straightforward. The next one, you'll plug in 1/3 for y and multiply it. But the other one equation is x plus 4y equals -1. You'll put 4/3, subtract it over, so you'll get -7/3, it looks like. And so there's your answer. Once you have the LU decomposition, the solution is simpler. The solution method is simpler. Okay? So you use this as a computational tool to help you solve the equation. All right, as far as homework goes, this is how we're going to go forward. If you want, this says it's due Monday, but it's not really due Monday. Because I thought I was going to give it out last time. If you want me to give you a grade on the homework, write grade at the top of the homework when you turn it in. If you just want feedback, write feedback at the top of the homework. And if you don't want to do the homework, don't. What I'll do in the grade book is that if you don't want the homework to count, I'll just exclude it out of the grade. Okay? So you'll still see it in the Moodle grade book, but I'll just exclude it. Okay? Sound fair for going forward? You can make the choice? Okay. All right.
Is it like every homework we have to do that?
Yeah, if you want it graded, yeah, absolutely.
Okay.
Yep. Just if you're gonna turn it in, just put in grade or feedback at the top, right at the top. And then I'll just, if you put feedback, I won't put a grade in the grade book. I'll just give you feedback on it. Okay?
Next homework, I put grade.
And then I'll put a grade in. Yep, you can do it for every single homework, and you can mix and match whatever you want to do. You can not turn one in. You can turn it in and say grade it. You can turn it in. It doesn't matter to me. Yep. Sound like a plan? All right. Enjoy. Sorry about the late time. Have a good one. Have a good weekend.